We're going to look at raw data using raw data in a hypothesis test. A new chemical process has been developed for producing gasoline. The company claims that this new process will increase the octane reading. 16 samples of gasoline produced with the new system are selected at random, and their octane ratings were 94, 93, etc. So we have 16 octane ratings from a random sample of 16 gasoline samples. Okay, the new system claims that it will increase the octane rating. The mean octane rating using the existing process is 93. The new system claims that it can increase the octane rating, which means the new system is going to produce octane ratings that are greater than 93. So based on that, is the company's claim correct? So the company claims that the new process will increase octane ratings. We have to see if it will truly significantly increase the octane rating. So the first part of the hypothesis test, where we state the null and alternative hypothesis all the way up to the decision rule, is identical in format to our last problem. Everything is the same until we get to the calculator, because this problem does not provide X bar and S, it provides raw data. So I'll show you what happens when we get to that point. Up to that point it's the same. The null hypothesis is going to be that the population mean octane rating is 93, meaning that the new system doesn't increase octane rating at all. It will produce an octane rating the same as the old system or the old process. So mu equals 93. The alternative hypothesis is that the population mean octane rating is greater than 93, which would imply that the new system produces octane ratings that are greater than the existing system, 93. Mu greater than 93. So there's our indication that we have a test on the right-hand side. This is a greater than test. So we have to identify the mean of the sampling distribution and its correct symbol. Our sampling distribution is a collection of sample means, and so the symbol is mu sub x bar equals 93. So it's the same as the mean of the population. Once you have that, you're going to be asked, is it based on the normal distribution or the t-distribution, and why? This problem, again, is based on the t-distribution. And the reasoning for this, because, if you read the problem, you're like, well, I don't have the population standard deviation, but I don't have the sample standard deviation either. What you do have is sample data, and from that sample data, you can figure out the sample standard deviation. So for that reason, you're going to be using the t-distribution. It's based on the t-distribution since sigma is not known. Okay, so that alone is a sufficient answer. But if you want to understand why we have the sample standard deviation, it's because we have the raw data for the sample, and when we have raw data, we can always find S, the sample standard deviation. Okay, you probably remember how we do this. You put the data in a list on the calculator and you run one variable statistics, and that will give you the sample standard deviation. The decision rule produces let's start with a picture that that has our significant tail shaded on the right because it's a greater than test. So we have alpha equal 1% shaded on the right. We're going to have our vertical line separating the reject region from the fail to reject region. And then we're going to label our center at mu sub x bar equals 93. Our decision rule is going to be reject the null hypothesis at alpha equal 1% if the p-value of the sample statistic is less than or equal to 0.01. So our decision rule has been the same every single time. The only thing that changes is whether or not you're using an alpha of 1% or an alpha of 5%. But other than that, the decision is always going to be to reject the null hypothesis if the p-value is smaller than alpha. Okay, a small p-value indicates that the sample statistic x bar is far away from the center of the distribution. So now we have to use a different method because we have raw data. So you're going to put the raw data in a list into the calculator, and I had mentioned that you can find the sample standard deviation with one var stats, but that's not what we're going to do. We're going to go to our calculator and put in the 16 sample octane readings. Stat, edit. Okay, I'm going to put the data here in L1. Okay, so make sure you do have 16 of them when you enter them. 94, 93, 97, 92, 96, 94, 95, 91, 98, 95, 92, 91, 95, 96, 97, 93. My calculator is lagging, but there it is. Okay, so 16 data values with 93 being the last one. This is what we're going to do now. We're going to go to the calculator's t-test function. And in t-test, you have an option at the top to choose data or stats. We've been using stats up to this point because we were given sigma and we were given S. But when you don't have sigma, you were given X bar. We were given X bar and we were given S. When you don't have either of those, when you have raw data, go over to the data entry and hit enter. And now you can enter data from the problem. The population mean is 93. The list that I'm using, my raw data is coming from L1. Frequency, you should leave at 1. Mu sub x bar, mu it's a test on the right hand side, so mu is greater than mu sub x bar. Calculate, hit enter. Okay, a couple things we have to note. The p-value, 0.0147 when rounded to 4 places. The sample mean, 94.31 when rounded to 2 places. And the sample standard deviation, 2.1823 when rounded to 4 places. So take note of that information, because on the handout, which is exactly the same as what you're going to see on the exam, you're asked for X bar. Okay, so the symbol of the sample statistic is X bar, and the value of the sample statistic is 94.31. Okay, so now you have those two. You're going to go and take a look at where 94.31 lies on the bell curve. It's somewhere on the right side of 93. When you figure out what the p-value is, which now at this point we already have, the p-value is all of the area that goes from this point up to positive infinity. So we found our p-value to be 0.0147, which according to our standards is small because it's smaller than 5%, but the conclusion is going to be to fail to reject the null hypothesis because this p-value is not smaller than 1%. This particular problem gave us an alpha of 1%, and when we compare that 1% to p, we see that p is bigger than 1%. So if you look at what alpha is and you look at what p is larger than alpha. So even though it's significant because it's less than 5%, it's larger than alpha, and so the conclusion is going to be to fail to reject the null hypothesis. If ever you have a p-value that's greater than alpha, you will fail to reject the null hypothesis. Because notice what it means. It means that x bar, which is at this location on the horizontal axis, isn't far enough over to the right to be significant in this case, to be very significant, because that's what the test was requiring. So our conclusion is to fail to reject HO at alpha equal 1%. We never accept HO. So the conclusion is either going to be to reject the null hypothesis and accept the alternative, or fail to reject the null hypothesis. So never accept HO. The question phrased was, is the company's claim that the new process will increase the gasoline octane rating correct? So you should recognize that when you fail to reject HO, you are stating that the new process is not significantly better than the old process. And so the new process stating that it will increase gasoline octane rating is incorrect. So no, the company's claim that the new process will increase gasoline octane rating is not correct. Okay, we're going to take a look at possible error again, because in this case, we don't have the same type of error that we had in the last example. Our actual state is going to be that the null hypothesis is true, which means that mu is equal to 93, or that HO is false and that mu is greater than 93. So one of these is true. Either mu is equal to 93 or mu is greater than 93. The decision that we make is that we can reject the null hypothesis, rejecting that mu is 93, or failing to reject the null hypothesis, failing to reject that mu is 93. Remember that if HO is true and we fail to reject it, we've made the right decision. If HO is false and we rejected it, we've made the right decision. Type 1 error is going to occur when we reject a true null hypothesis. It means that the mean octane rating is 93, but we rejected it. A type 2 error is going to occur when we fail to reject a false null hypothesis, meaning that the octane rating is really greater than 93, but we failed to reject it. We failed to reject the null hypothesis. So in this problem, because our conclusion was to fail to reject the null hypothesis, the type of error that could have been made is a type 2 error. Okay, a type 2 error occurs when we incorrectly fail to reject a false null hypothesis. So in this test, we could have made a type 2 error. And what it means is, if the mean octane rating or the mean octane level with the new process really is significantly greater than 93, but we've incorrectly failed to reject the mean of 93, we've made a type 2 error. Okay? So it's possible to make a type 2 error when you fail to reject the null hypothesis. It's possible to make a type 1 error when you reject the null hypothesis. So understanding those two scenarios and being able to recreate the chart will help you answer questions like those. You have a web work question on this topic, and If you have any questions on it, please email me. I understand that this is one of the more difficult topics in the course, so I will be happy to help you if you want assistance with this. I'll see you at the next lecture.